Great. So today we're going to start looking at vectors. Okay, as I said, vectors, we're going to split it into probably about 3 days worth of stuff. For this week and what we do next week, okay, I'm going to use a different book. Okay, so all the homework assignments, again, they're in the back of the packets that I'm going to give you, and I'll have another packet for you next week with the other parts on vectors. Okay, so first thing we'll do is just define what a vector is, okay, what it's used for. A vector is a quantity that models two things. Does anybody know what the two things are that a vector models? Yeah?
Magnitude and direction.
Yeah, a magnitude and a direction. All right, so what's an example of something in real life that has a magnitude and it also has a direction? Okay. Yeah, Kyle?
Earthquake?
Or
maybe not direction, but...
Well, earthquakes kind of, I guess they propagate out from a central point, so they kind of spread in multiple directions. We're kind of thinking of something that just goes in one direction at a time, just going in one direction.
Like you're using a GPS that says take a route, go 6 miles north.
All right, so maybe something to do with travel in general. If you think about like your car, you might be driving in a certain direction and going a certain speed. There's your magnitude and your direction, okay, in a car. Yeah. How about other things? Yeah?
If you throw a ball.
Yeah, if you throw an object, there's a certain direction you throw it and a certain speed. Okay, so that's an example. Yeah?
Planes.
Yeah, planes. So these are all examples of velocity vectors. Cars throwing an object, an airplane, they travel at a certain speed and they travel in a certain direction. Okay, force is also a vector, but it's not a velocity vector. Okay, when you have a force, it might be like how hard you're pushing on something and the direction you're pushing. Are you pushing on it down? Are you pushing up? And how hard? All right, so I have an example just to look at here with planes. Okay. If you think of planes as vectors, okay, they're all traveling in different directions, and they all have different speeds. Okay? And when you have a plane, somebody has to keep track of all these vectors, right, to make sure that, obviously, collisions don't happen. What's a little more complicated is we have to think three-dimensionally. So on the screen, you might see two planes that look like this one and this one. They're heading towards each other, but one of these planes might be at an altitude of, say, 1,700 feet right now. Okay, and the other plane is at an altitude of, I guess this plane has already landed. So it's a little out of date. But the point is, if they were both in the air, they'd probably be at very different altitudes. Okay, and it doesn't look very confusing. Okay, if you look in this area, it doesn't look like there's that many flights. But the further that you zoom out, if I can zoom out, let's see. Can I zoom out? Let's see. There we go. Thank you. Okay, as you start to zoom out, you can really see some of the traffic. And you'll start to see the airports, where like there's New York City. Okay, down New York City's right here. Okay, that's like the DC area or Pennsylvania. DC might be, let's see, down.
New Jersey's right where you.
Yeah, probably right in here. All right, so you can start to see some of the confusion and possibly the complexity in organizing all these airplanes, but a vector is a good way to think of them. Each one of them has a speed and it has a direction. Okay, and using that, they can control airplane traffic. Okay, so that's one use for vectors. All right, so we can represent vectors using an arrow. Okay, it's not always the most efficient way, but it is how we're going to start looking at vectors visually. Eventually, we're going to get away from the visuals and just do pure mathematics, just numbers. Okay, but we'll start with arrows. Okay, an arrow works well because you can represent two things with it very easily. You can represent magnitude, okay, with the length of the arrow, and you can have a direction just based on which way the arrow is pointing. Okay, so the length is going to represent the magnitude, and which way it points is your direction. Okay, on that other screen with the airplanes, they didn't really do it that way. They do have the plane flying in a certain direction, but they don't stretch the plane out if it's going faster. Okay, they just show the plane. Right, but we will have longer and shorter arrows depending on the magnitude. Right, so when we draw a vector, it has 2 points. Okay, what we call an initial point. That's where it starts from. And we have a terminal point. That's where it ends. Right? And it does make a difference if you switch them, okay? Because the direction is important. If I were to switch my initial and terminal point, what effect would that have on the magnitude?
Well, if the terminal point is farther away,
I keep them in the same spots, but literally just switch which one is initial and which one's terminal.
Would something become like negative or something?
Okay, we were representing it as a number. Something would become a negative, but would that represent a change in direction or magnitude?
Oh, would be just a change in direction.
That's just a change in direction. Okay, if you switch your initial and terminal point, that doesn't affect your magnitude. So if you're traveling 60 miles per hour east and you switch your initial and terminal point, now you're traveling 60 miles an hour west. That's all that changes, direction. Okay. Sometimes we can also symbolize a vector by a single letter. And if you look in the packet I gave you, they do it 2 different ways. One is a letter with an arrow over it pointing to the right. The arrow on top has nothing to do with the direction the vector is going in. This whole symbol just means you have a vector. Doesn't mean it's going to the right. Just this is vector M. And another way you can see vectors written is with a bold letter. And if you look in your packet right on the first page, they show several examples of vectors with a bold letter. Any questions on the 2 ways we can symbolize a vector with a letter? Okay, I'll probably do a mixture of both ways. Bold letters takes me a little longer to write, but the vector where I put the arrow on top, that symbol, that's a little quicker. Hey, does anyone have those 2 symbols? All right, so first thing to understand is what happens when we combine vectors together. Well, when you combine vectors together, you get a new vector. Right? One way to think of it is like, let's say you had a box, okay, which we're just going to represent as a point. Right? And you're pushing right on the box. And then you have a friend that's pushing up on the box. Right? So if you both did that at the same time, what would happen? What direction would the box move in? Yeah. It would move in a new direction, up and to the right, and it would move at a new speed. Right? If you were both pushing to the right on the box, then what that would happen is it's like you're working together. You're pushing right, your other friend's pushing right, so now the box is going to move to the right even faster. Okay? It's going to, because you have more force. Okay, so when you combine vectors, you get a new vector. Right, so let's take a look at how we can add vectors graphically. To do this, you really need graph paper. Okay. And the way you add vectors visually is you have to position them a certain way. Okay. Let me show you visually how you do it first, and then I'll describe it in writing. Okay. You basically put one vector like that, and put the other vector like that. That's it. So you connect the end of one to the beginning of the other. Okay.
Does it matter where in the graph?
No, you can put it anywhere you want in the graph. Right? So to describe it in words, it's a little bit more words to say it, but you make it so that the terminal point of V is right on top of the initial point of W, just like I did. Okay, so you line them up so the terminal point of your first one and the starting point of your second one are right on top of each other. Okay, so that's the first step. So I'm going to take V, and then I'm going to add W on to the end. All right, now how to look at that picture and get my final answer? We're going to draw an arrow, or a vector, from the initial point of V to the terminal point of W. Okay, so we're going to draw a vector from the initial point of V to the terminal point of W. Okay, and let's actually use an arrow. Just like that. Okay, so now if I move it off so you can see it. That arrow that I just drew, that's V plus W. Visually. Okay, any question on what I did there? Okay, and it doesn't matter where you do it. I mean, you actually, I guess for this one, you don't even really need graph paper unless you're trying to measure something about the length of it. But you could do it just on blank paper. You know, just draw your arrow in. All right, so that's how you add two vectors visually. All right, so it does require you to have graph paper and something to try to draw a straight arrow. All right. What do you think is going to happen when I try to add these two vectors? Yeah, they basically cancel each other out. Okay. Here's V. Right? So I'm going to take and line these up. Okay. But what happens if I put the ending point of one lined up with the starting point of the other? Okay, I'm going to erase those 2 points, but that's the 2 points I'm going to line up. Okay. Watch what happens. Now I need to connect my starting point, okay, of one to the ending point of the other, but they're the same point. Okay. Does everybody see that? All right. So now you would connect start point to end point, but that means you'd be connecting this point to this point. So those two vectors cancel each other out. Right? And what ends up happening is we get what's called the zero vector. Okay, I can't draw a picture of that because there is no picture. But we can't write 0 the number, because the answer here is, we already said when you combine two vectors, you always get what? A new vector. You don't get a number. You get a vector. So this symbol is called the 0 vector. Okay, it's a vector that has no direction. It's the only vector that has no direction, and it has no magnitude. No magnitude. And you could also write it this way. Make it a bold 0, but I think that's going to be confusing if I'm trying to tell if you made a bold 0 or the number 0. So I would probably put the arrow on top. All right. Vector addition is both commutative and associative. And I think for this part, if you write this down, That's probably all you need to write. You can watch me prove why it's true. Okay, this part is very hard to write down. I need to move things around to show you. Okay. Commutative means I can change the order, okay, that I add two things up in. Okay, so here's V. And then if I put W on the end of it, and then connect where I started to where I stopped. Okay? That's V plus W. Any questions on that? All right, now I'm going to switch it. I'm going to take W and I'm going to add V onto the end of it. Okay, so now I have W first and then V on the end. But if you look, it's exactly the same thing. Right? So when you're adding vectors, whether you do W and then put V on the end, or do V and then put W on the end, it doesn't make a difference. It's commutative. Okay. It's also associative. And associative just means you can change the order you add them up in. I think to save time, I'm not going to go through the visual of this. But what I'd have to do is take A, then add B onto the end of it, then take and add C onto the end of that. If I was doing it the way on the right, I would take B and I would add C to it first. I would do B plus C first, and then I would take A and add that answer onto the end of it. Okay? No matter which way I do it, it's going to come out the same. Right? So you can change the grouping when you're adding vectors. It is associative. Right? And that's very similar to doing something like this. Just like your associative property with numbers. 3 plus 3 is 6. 1 plus 5 is also 6. Okay, so any question on the idea of associative? Okay. So we'll save time. We don't have to go through that one. What's the difference between these two vectors? Okay, so what's the effect of that?
Different direction.
It's a different direction? Can anyone be even more specific than the negative direction?
Going down, opposite direction.
I'm thinking of a word here that, because for example, going up and going left are different directions. But these are even more specific. They're opposite directions. All right, so if V is up, negative V is down. Okay, they're opposite directions. What do they have the same, though? What do they share?
Initial point.
Actually, in this case, the initial points and terminal points would be switched. Okay, so if one had an initial point on the left and a terminal point on the right, that would switch for negative V. They would switch places. But we talked, I think I mentioned this earlier.
They have the same magnitude.
Yeah, they have the same magnitude. Okay, so the only difference between V and negative V is the direction. Same magnitude. I gave you guys a problem like that a minute ago. This one. These were exactly this. These vectors is what I just said. One's V, one's its opposite, negative V. Okay. And when you add two vectors that are opposites, you get a new vector called zero vector. So the next thing we're going to look at doing visually is subtracting two vectors. Well, the way I want to think of subtraction, we're going to really do it like addition. So to subtract, what I'm going to do is find the opposite of the second vector and add. All right? So if you want to think about it like numbers, instead of doing this, I'm going to do this. I'm going to find the opposite of the second vector and then add. Because we already know how to add vectors. So really what that means is all we have to do is make one vector negative. Okay? Make it point the other way, and then add it. That's like subtracting. Any question on that idea? So we're going to make one vector negative and add it. Just like we did with numbers here. Make the 2 negative and add it, and it's the same thing as doing subtraction. All right. So how am I going to think of v minus w? I want to think of it with an addition sign. Yeah, we're going to think of it as v plus negative w. So v plus the opposite of w. What does that mean I need to do before I can subtract them? What do I need to find? The opposite of? Yeah, so let's find the opposite of w. Okay, and if you're doing it on paper, just draw it the other way. But I can use my smartboard and flip it twice, and it'll make it exactly the same length and point the other way. All right, so there's negative w. Now take v plus negative w, and now it's like I subtracted them. So my answer is right about there. So that's v minus w. Okay, any question on that one?
So all our answers are going to be for an arrow with w.
Yeah, you're going to have, I'll show you what a test question is going to look like. But what it might be is, if it was multiple choice, I'll give you 4 choices, and you'll have to pick which one is correct.
Right.
So if I was going to give you 4 choices, I might give you this as a choice. I might give you that as a choice. And then I just might make up 2 other ones. That one and that one. So in this case, that would be the correct choice. Now if it was set up like that. Okay. Questions on that? All right, what does it mean to scale something? Usually when you scale, it has to do with measuring. But like if I said, I want to make a scale drawing or a scale model, what does scale in that case mean? Yeah?
It's what's
It's what? Like a model? And what is, how does the model compare to the original usually? Yeah, a smaller version. It's identical, except it's smaller. Or you could make a larger version. Okay, so maybe if you were making a diagram of a cell, you might make a large version, like on a box, so people can see it. Okay, it's a larger version of a cell. All right, so when we multiply a vector by a number, what that does is it scales the vector. And the result is a new vector, but it can be longer or it can be shorter. If you scale it by a number bigger than 1, what do you think that's going to do? Make it longer or shorter? Longer. How about if you scale it by a number that's a decimal, like 0.5? Shorter. What would happen if you scaled it by a negative number? What's the negative going to do? Flip it. Yeah. So what can happen when you scale a vector is really 3 things. It can become longer, it can become shorter, and a negative could also cause it to flip. Okay, so that's what I just said. You can shorten, lengthen, or reverse the direction of a vector. So a scalar can shorten, lengthen, or reverse direction. All right. So here they've given me v. I want to find 2v. Did anyone, before I even do it, anybody explain how is 2v going to compare to v? Twice as long. What about direction?
Same direction.
Yeah, same direction. It's just going to be twice as long. Right, so find 2v. Very easy. Just take v. Take another v. Put them together. And that's basically it. There's 2v. Okay, to find 1/2 v, I don't really have a way on the smartboard of cutting something in half, so I'm just going to estimate it. If I had graph paper or did it on a graph, then I could do it exact. Okay, but I would say that's about 1/2 v. All right, how am I going to find -1v?
Opposite direction.
Yeah, it's just going to be the opposite direction. Okay, I think these letters are actually bold, but since I'm zoomed out, you can't really tell. If I make it single page, you can tell it. I tried to make it look bold, but when I'm zoomed out, you can't see it. So that's why I'm putting the arrows above them. All right, so yeah, -v. Just take that, clone it, and then on my board, I can just flip it vertically. Whoops. Flip it vertically and flip it horizontally. And that switches the direction.
That's the same direction always.
Yeah, I guess I didn't flip it right. Flip it horizontally, and flip it vertically. I think I pressed the wrong thing. Thank you. So now it's exact same magnitude, just points the other way. What are the two things that would happen with -1/3 v? It's going to flip, so I'm going to use this one. And it's going to shorten. Yeah, so just estimate 1/3 the length. Maybe about like that. So there's -1/3 v. Right. Let me just show you how to do one of these. To find 2v plus 3w, okay, what I do is just pick a starting point. Okay, it's a little tricky because you can go off the grid, but I think since w is going to go down that way, I should be okay. It says I need 2 of the v's, so just go like that, put 2 v's together, and now take 3 w's. Just put those on the end. And that's how you do 2v plus 3w. And then just connect it. Right? It does require a little planning if you're trying to stay on the grid. If you're not trying to stay on a grid, then it's just make sure you have enough paper to you don't go off the edge of your paper. Any questions on that one? All right. Okay, so if you have a vector, okay, and they put this symbol, these double bars around it, what's that? Kind of like absolute value, except it means they want the magnitude. Okay, so if you ever see a vector and they put these symbols around it, it means all they want you to talk about or find is its magnitude. So this would just be like 10, okay, however long the vector is. Okay. Today, you don't have to worry about finding lengths. I just want you to know what the symbol is. Okay, it's double bars around it. And of course, because it's magnitude, it's a length. Length can never be negative. So, what would be the difference between the magnitude of vector v and the magnitude of the vector negative v?
There is none.
There is none. This is the same thing. They're the same. It doesn't matter what direction it's pointing in. Magnitude is just how long is it. And negative v and positive v, same length. If the magnitude of a vector comes out to exactly 1, we call that a unit vector. So if a vector, when we talk about how to find the length, if we find it, comes out to exactly 1, it's called a unit vector. And I think this is our last thing. Right, so if we're going to start to do algebraic operations on vectors, we need a better way than drawing them. Drawing vectors is going to take forever, right? It is fun, yeah. So this is a notation you can use to write a vector. And I'll show you an example of one on the next page. 2, 3, that's a vector. Okay. What the 2 and what the 3 are the horizontal and vertical components. Right? So what it really tells you is A tells you from a start point, how many units do you go from that start point, left or right? Yeah, in this case we go 2 to the right. And B tells us how many units up or down. Yeah, so it's, in this case, again, that's your horizontal. That's your vertical. Okay, A is the horizontal. B is the vertical. So in this case, I pick a start point. I go right 2. I go up 3. And that's my vector. The thing that it doesn't tell you is where to start. I could start here. I could start right 2, up 3. I could put it over here. Right 2, up 3. It doesn't tell me where to start. There is a place that's pretty common to start. The origin. Okay, that's the best place to start. Okay, at the origin. Right, and if you decide to start your vector at the origin, okay, that's called a position vector. Okay, so the only one that's a position vector here is that one. Right, and the last thing is if they give you an initial point and they give you a terminal point and they say find the position vector. Right? So they're telling me where it starts, they're telling me where it stops. I can tell it's not a position vector because that's not 0, 0. It's got to be 0, 0 to be a position vector. Okay? The way you find the position vector is you label these and plug them into that formula. In this case, it would be x2 minus x1, comma, y2 minus y1. And that is our vector. Yep. So in other words, if you started at the origin, you would go 5 right and 4 up. Okay, so that's your formula for finding a position vector. Okay, so on the test, I will ask you to find a position vector. So make sure you copy down that formula or copy the example. Either way. All right. So I'm just going to put up the homework so people can copy that. And if you need to see this, I can put it back up or you can grab it offline. Okay, so the homework is on 344. Okay, you might need the graph paper, so hang on to that. And it's 1 to 10 all. 14 to 22, just the evens. 26 to 32, just the evens. And don't follow the directions they give you on 26 to 32. just find the position vector on 26 to 32. So we'll go over that tomorrow, and then we'll have our test.